Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to NPTEL course on Groundwater Hydrology and Management. This is week 9, lecture 1. In this week, we have been noticing some groundwater concepts and how to construct a groundwater aquifer layer understanding. In the previous weeks, we have been looking at the concepts of groundwater hydrology, the parameters that are important, and most importantly, we were looking at the access and recharge discharge. What will we be doing this week? Let's see in a more constructed manner. First, let's do a recap of week 8 and how it's linked to week 9. In week 8, we looked at groundwater access as a problem. How does groundwater being accessed? Everyone knows by now that India is the key groundwater extractor in the world, extracting about 245 to 265 kilometer cube water annually. And there is tremendous stress on the aquifer. How are the water access? It is accessed through the groundwater pumps. So we looked at each concept of where the groundwater access is mostly happening. What are the key uses through wells, dug wells, driven wells, or drilled wells? And then we looked at the different pumps that are used, low suction pump, high suction pump, and manual or treadle pumps kind of things. We noticed that as per the use, as per the demand, the well type and the pump type differs. Then we looked at the source of energy for the pump. And most importantly, we noticed the pump energy is unsustainable because it uses a lot of diesel or electricity. These are not from renewable sources. And that's why I'm saying it is not sustainable for long term. Also, they lead pollution to the environment because diesel pumping has a lot of issues. So what has happened is there has been considerable action on the ground in converting these pumps to more eco-friendly pumps. Example, sustainable resources like solar, windmill, manual and livestock. You would see cows in villages which would go around and round, and then they would churn a gear which pulls up water. And solar pumps is very common nowadays, along with wind-powered pumps. On the whole, we notice that the access is increasing, the type of pumps are increasing, and there's also some renewable sources coming in. So now we are going to leave this phase of the course where we looked at the components, the recharge, discharge, and access to the water. And now we're going to construct the aquifer itself. How is the aquifer constructed? How do we know what layers are there? How do you know which water we're going to use? Okay, that we're going to look at in this week onwards. So from this week onwards, we'll be looking at the aquifer layers, how you estimate these aquifer layers, what is the data that is needed, how do you get the data, where do you get the data, and what are the steps in creating your first kind of conceptual model. So we'll be looking at boreholes and bore logs and data associated with it. Where in borehole, we already saw in the groundwater access slides, where I was talking about drilling wells, right? Drilled wells where there is a motor which comes and drills. And then you have a bore hole, which becomes a well. So from the data you collect from point 1, we will be establishing the layers of the aquifer, which is called stratification of aquifer. And we'll be using Central Groundwater Board data and the State Water Board data to understand the groundwater level fluctuations where the data is available. So it is more about where is the data available, because establishing the water level, the head, everything has been taught in class. Then we'll also look at WRIS data. Where do you get this data? What data is available? How do you access this data, etc. Then I'll explain one satellite which is very unique, very special satellite called GRACE. This is the only satellite that actually monitors groundwater from space. So I'll show you what is the principle it works. And those who have knowledge of GIS and remote sensing can easily download it. Now with all these data, you can understand how this map is created by the Central Groundwater Board, which is an aquifer map. Because it is not only created by the layerings which is happening, but also the data which is taken at different depths, and the dominant aquifer is mapped for India. Okay, so let's move on to today's lecture, which is the boreholes and bore logs. As I said in the groundwater access slides, we looked at this truck coming in and putting a drill into the ground and then adding columns to it and digging very deep, mostly the deep aquifers. It goes to a couple of meters. And this method was called the drilling method, right? So while you're drilling, I told that there's a lot of debris that come out, the rocks, the sediment, the water. You can see here it comes out. But what do you do that is it doesn't come out by itself. You have to pull it out, right? You pull it through the auger, you pull it through the drill bit. So here at this bottom, you have a drill bit, which is looking something like this. Okay, it looks like an X mark or a very irregular shape, like a blade of your mixie. Okay, take a mixie, just visualize it, that you attach it at the bottom and it spins. When it spins, it eats out the rock, the layers on the side, and then you take it out. Now, if you take it in regular samples, the depth of this rock type by the motors, etc., you can establish what layers are present in the aquifer. We are not able to do that now. Why? Because most of the time what happens is when a farmer needs a well, he calls this truck. The people go there, they put down the instrument, they add the columns, drill, take the debris out and go. There is no documentation at regular intervals what soil is coming out, what rock type is coming out, and what water is coming out, because the water may be salty. They'll just take it and drink and say, oh, it is bad, it is good, and then they do some test and then they give it. But most probably you should also take the rock samples and understand what is the property. Okay, and that is like your soil analysis. So just for the sake of how soil is done, I'm going to show you some slides so that you can now relate between the soil and how the deep aquifer rocks, aquifer types are done. So how is soil studied? How do you take a soil sample? You take an auger method. Okay, you have this drilling method, and then the top you have a drill, which is you just rotate and it goes in. And you pick the depths at which the instrument should go in. Okay, inside the instrument there is a column, a steel column, a steel pipe. Okay, it's basically a steel pipe which is cylindrical. Okay, and it collects soil. So when you drill, this cylinder will be pushed inside and then it takes the sample out. Okay, and then this sample is then taken to the lab and analyzed for chemical and physical properties. But then here what happens is you have at different depths also you can take. Can this be done for deep aquifers, for aquifer mapping? No, because you cannot hand drill it to that deep. So this is one way of doing the sampling. What is the other way? They use an excavator, they dig a big hole. Okay, they dig a big hole and then you go inside. You can see the scientist here. He goes in with the ladder and then he pushes a small auger or cylinder inside. So you can see the cylinder, it goes inside, takes a sample out. So at different depths, they will measure. So you can see a pipe which is being used to measure different depths. He will go inside different depths and take the sample and come out. Now the sample is then tested for chemical and physical properties. The idea is, can you do this for aquifers? No, you cannot, but you need it. So why do they need to do different steps, different depths? Is because they want to understand how the material changes. Similarly, you need to do it for aquifers, especially for aquifers, to understand where the water is and where the water is held in the aquifer. So that is where you need heavy artillery or heavy machinery. Okay, samplings at regular intervals is very much needed and at varying depths. What you see here is the same drilling machine which has to be parked, and instead of drilling for water, now you're going to drill for the sample, the soil at the top and the different rock and other materials at the bottom. Then each sample is taken to the lab, as you can see here, for physical and chemical property assessments. They take the sample, push it inside the lab containers, and they do the experiments. So what happens is, when you push this rod and then take a sample out, you will have different depths of rods. Okay, so the rod is taken like this. First, you push one rod in, take the sample, and then you attach another rod, push it in, take the sample, because the depth is going to increase. The thickness is almost the same, what you take out, what you can take out, because sometimes the rocks won't go in, so you'll see less samples in it. But our idea is, from A to B, what is the dominant rock type? What is the dominant soil type? I'll take it out, and then I do a visual inspection. The visual inspection can be used to understand the texture, which is the combination of sand, silt, and clay, or individual items. Is it sandy, is it silty, or clay? Then it is used to understand the structure. Just looking at it, they'll know, is it platy, is it prismatic, is it like grainy or bulky, those kind of things. These data are important first visually to understand how deep one should go. Because if you're going to see all very hard rocks like this, there's no point in going more and more deep, because your instrument will face technical problems and there will not be any water. So at the end of the day, you're mapping for water, not for oil or not for rock. This is purely for aquifer mapping. Okay. If you go to a geology course, you'll have different depths. You'll go very, very deep, even kilometers deep. Here we go 600 meters, those kind of things. So then some of the samples from here are taken to the lab for lab test, wherein nutrients are analyzed, nutrients as in chemicals. For example, if this material has a lot of arsenic, then you should be understanding that arsenic can mix in the water. Same way, if it has fluorides or iron content, then the water is mixed with this content because of geogenic contamination. It's unfortunate, you'll see this is the water people drink in villages because they don't have other resources. So that is why groundwater management is an important course. If you understand these layers of soil and rock, if you understand the chemical properties of it, you can tell the people like, don't drink the water. Okay, so the lab test should be done. Then the porosity, the physical parameters of porosity, bulk density, specific yield, specific retention, hydraulic conductivity, everything is estimated. All these have already been taught in class. All you have to do is go back to your notes, check what these properties are. And now I'm going to show how these samples are taken for these tests. Because now slowly we're coming to the end where we're going to look at data, construct an aquifer, and then say how to read an aquifer map. Then we'll go to case studies. Okay. because we have only 3 more weeks. So moving on, you can take these samples to the lab and get it tested for nutrients and porosity, physical parameters, chemical parameters, and you can establish a record of what is happening at each drill spot. Is this happening in this when you do the water level analysis? No, it should happen. But however, they don't have time. As I was mentioning, if you give them a sheet and say, okay, document every 5 meters, what is the rock, what is the water, take a sample, put it in a bag, they don't have time. They said, no, sir, I have to go to another well to put another well. They'll come to that location. Either you give a location or they look at the surrounding and say, okay, here's where the water could be. They put and then take the sample out, drill, and then go to the next drill and go on. There is no data available. It's not only here, but most countries. They should be having a log, but they only have a log of where they put the wells, but not what type of rock, what water came, etc. They should maintain it regularly. So moving on, let's now see what we can do. How do you enter it in a piece of paper or a data sheet? So this is called a bore log sheet, wherein you enter the data of the samples that you took. Okay, let's go through what the columns read. The first column is your drilling method. Okay, there is only one machine, but the drill bit, what you attach at the bottom may be different depending on the depth and depending on the rock. So initially you start with the ADV, which is a auger drilling. V is a bit. So bit is that mixie component, as I said, right? The blade. So that blade and an auger type of blade with a drilling bit is sent in. Okay. And mostly that auger type is only for the shallow aquifers or unconfined aquifers. Then when you go deeper and deeper, you use the WT method. Okay. Where W is the wash bore and T is TC bit. The bit changes. It's not the V bit, not the V-shaped bit, but maybe TC bit. I'm not getting into the engineering of this, of the designs and stuff. All you have to know is when you have a mixie and when you put, for example, tomatoes and fruits, you use one blade. And then when you throw the juice out and then you put hard things like coconut, pepper, and those kind of things, then your mother uses a different kind of a blade, right? So that blade differs not because of the mixie, but what you have to put in. Same here. The bit will differ based on the rock type. If you want a carpentry, if you're using it on wood, you use one bit. If you're using it on a steel drill, you will use a different bit. Okay. Basically, the bit is, maybe I can draw it just for understanding. So this is your drill, the thick thing that you have. Okay. The instrument, like your drill, we had a drive point, you had to hit it, right? So the nail, kind of, this is the nail part. Maybe I can draw it again. This is the nail part, and then here you can have different types of sharp mixie components, as I said, the blades, and that is what is changing here, the drilling method. Moving on, then we go to the sample type. Here, all these samples are taken in an undisturbed 50 millimeter diameter cylinder. It is called U50. So basically, you slowly push this cylindrical container, which is 50 millimeters in diameter, and then you take a sample out, keep it separately, and then you go again, drill, take a sample, drill, take a sample, and go like that. So you could see here, almost they took 1, 2, 3, 4, 5, 6, 7, 8, 9 samples in 11.8 meter depth. So almost 1 meter once they would take a sample. Now think, does the person who comes for water, for putting a well, bore well, do they have this time? They don't. But they should be documenting it because the data is missing now. Throughout India, you have so many bore wells, but we do not have bore logs. There's no data about what these wells are. Okay, so every meter you take a sample and keep it separately like this. So this is every meter one sample. Then you go and say where the water depth is. So here the water depth was just 1 meter below the surface. So that is good. Okay, so the water is set, but still you drill and see what the material is. And this is the depth, as I said. And it, as I was initiating in the previous slide, and here it was stopped at 11.8 meters. So after 11.8 meters depth, the machine would not have gone in, or you were constrained for power or depth of the tool, and or you found something very straightforward that it is not going to change. Like for here, the graphic of the log, the visual interpretation, the physical interpretation, lab interpretation is now drawn in the sheet of paper saying from the top to 0, maybe half a meter, you have silt, clay, low, medium plastic thing, and you can see a legend is used. Then a crossbar diagram legend is used to say from about 50, not 50 meters, sorry, it is 0.5 meters. So 0 to 0.5 meter is silty clay. Then from 0.5 meters to around 10 meters, it is silty clay high plasticity, with a trace of lime, grain, sands, some organic matter. Why is organic matter present? Because it is the top. At the top, you should understand that there is some decay happening. The plants, the trees, the leaves, right? And sunlight and water are acting. So there is some decay, and that decay of organic matter is on the top soil. When you go down from around 9.5 meters to 11 meters, it is only sandy silt clay, medium plasticity, gray color, 25% fine grain. So after that, maybe the person drilling, the scientist would say, no, it's enough because it won't change. It's only bedrock going to come, and the water is enough. So this depth 11 meters water is enough. So let's stop here and then take the sample. Okay, right. Take enough with the sampling. So that is the 2-3 columns that we saw. Then what happens is the material description as we went, every description, the visual, the texture, the chemical properties can be put here. It can be left some space so that you can add after your lab visit. Then the moisture, you take a sample and then say, is the water having, is the soil or the material having water? Okay. And that is given as M for moist and W for wet. So why is the top moist and below wet? Because the top might be evaporated. Plants and animals act on it also. They graze and then stuff. But most importantly, wind is acting, so sunlight is there, so it dries, evaporates. Whereas the bottom, right below the bottom of the top soil, which is only a couple of centimeters deep, you have a wet soil and rock type. Then when you go down, again, it becomes moist. It's not wet, not fully water, but moist. Again, why is also wet? Because the water table is there. Once the water table is there, all the pores are filled with water. There is no vacant space for air to be present. So it's not moist, it is wet. And again, please see that at this depth, it is the water table. But why are we having wet here? Because dominant layer is what we have to say. Every meter you take a sample, not every centimeter. So every meter you take a sample, and throughout it, you can say it is dominant species, because you cannot afford to do sampling at every meter, every centimeter or every millimeter, right? So you have to take one chunk and say this is the dominant species. The next column gives you the consistency of the material. Is it ST, which is stiff, or VS, which is very soft, and then FST, which is firm and stiff. Stiff means very hard, okay? And if it is firm, it is extra hard, more like it is the parent material. So you don't want to go deeper than that. So the borehole is the hole that you dig for the well, and the sample you take out can be called a borehole sample or a bore log sample. Okay. So additional abbreviations and observations can be also taken, like PP, which is the pocket penetrometer, to understand what is the pressure, how much pressure you should be exerting to get in. Okay. I have another slide to show what exactly these mean and how it is useful. Because for here you can see the pressure to go in is very less, 20 kilopascals. But when you go down further and further, the penetration is going to be very tough. And that is where you stop. Otherwise, your drill bits will break, your instruments will break, your technical issues will come, and it's better to stop, because the physical understanding is also, you are good now, you know the water. Here, we're not drilling for petrol. Here, we're not drilling for rock types. Here, we're drilling for aquifer types, okay, which is a mix of rock type and the water availability. So this is a one well you take and you put a sample of the sheet. So now let's look a comparison between wells. Each one is one site, okay, but in the same area, same boundary of the study site. What they have done is, for example, Nick et al., they have taken a sample and categorized the material at each depth, okay. So the zero is the same, and from zero they found that the first sample has a lot of clay on the top, and then when you move down there is some sandy clay, okay, followed by thick sand, and then some sand with gravel or gravelly sand, and then we go down more clay, silty clay. Whereas some meters apart, you have only clay, and then you have sandy clay, again pure clay, on top of it is silty clay, and then silty clay. Then you hear almost homogeneously it is clay. So what is happening here is there is variations. So what do you read from a single borehole analysis? That is what is important. And also tell about what is the standard penetration test. So this study, for each well, they've also measured the standard penetration test along with the water table. So what does the standard penetration test give you? It gives you the resistance of penetration, which means higher the resistance. If it is high resistance, you cannot penetrate in. If it is low, then you can penetrate through and the drill can work. Okay, so it is a very standard test. So what they've done is, when they moved down, you could see in the first, let's go each sample by sample. When the first sample, they went down, after 10 meters depth, they could see a sudden jump in the penetration resistance, okay, and then it becomes stable. So once you hit a stable rock, a stable penetration, most probably you will give up, because you say that it doesn't change, and also it is very high, 50, okay. The penetration test is at 50, they'll normally stop, because after that you won't have much differences, you won't have much water. The same is happening for the second. Here the depth is much less. Here they drilled for 73 meters, but here you could see that they drilled, and then suddenly it rises to 30, 40, and then 50. When it goes above 50, they stop. It's like a metric they have. If you go above 50, don't drill it, it will break, or there's no water going to be there. Because if it is going to be hard for penetrating, how is water going to go there and stir, right? So that is the part, but they try to see, maybe it is an aquitard. It was an impervious layer. And then when you go into the impervious layer, there's water. They'll try, they go like a couple of 10 meters deep, but then if they see no changes, they stop. Same thing here, from a clay layer, they go and suddenly there is an aquitard or an impervious layer. So suddenly the penetration jumps, okay? But below the penetration test also, or below the aquitard also, there is a very thick, solid rock, and so it just keeps on increasing. After 50, they stop. So what you see interesting here is that the depth is changing. The depth from which on the top they dig is changing. They stop, the stopping point is changing, because they now understand that it is maybe an undulating surface like this, and the bedrock is reached. No more water is going to be there. Let's stop. Okay. So from the surface, it might be the same. On the top, it all looks the same. But when you go down, there is variations. So what does these analysis show you? It shows you that the single borehole analysis, the single bore, variations between the layers, between the depths. So as the depth changes, there is some variations. It also shows homogeneity. So for example, from 15 meters to 73 meters, it is the same. So the same log shows you variations and homogeneity, isotropy and anisotropy, which is all discussed in the previous lectures. Isotropy means it changes per the direction, along the direction it doesn't change or change the property. Okay, XYZ we discussed. And then the key layers. The key layers are also identified because the dominant layers are taken and mapped in this board log graphics. So all this is important, okay? But how does it tie with other logs is also important, right? So each log will have potential reasons why this particular layer is there and why water is there, because of the porosity, the nutrient property, the physical properties, hydraulic conductivity, specific yield, etc. There is also limitations. Let's quickly look at what are the limitations. Selection of sites. How do you pick this point is a limitation. What science have you used to say, okay, this point we're going to drill and take? A lot of people don't have that understanding. They just randomly dig and then say, okay, I'm going to take a sample. How do you relate between sites is also missing. Okay. The depth, how deep you go can be limited by your understanding or by your technical measurement device. But maybe there is water underneath, we don't know. Okay, so that depth is also limiting. How does it vary between sites? There is less understanding of it. So why does clay come here, whereas less clay is here? They don't understand. Okay, when they drill, I'm saying. So that is a limitation. Why they don't do these drill log experiments. But we will see this in the next class. How do these individual single layers talk to each other, and a beautiful aquifer map can be done, will be analyzed in the next lecture. I will see you with that in the next session. Thank you.